Hi. This talk started out of a Twitter conversation. I haven't decided whether to be embarrassed about that or not. But I was on Twitter one day, and a relatively prominent left-of-center pundit piped up and said, you know, climate change seems like a really big deal. Why are so few people talking about it? Why have so few thought leaders made it their signature issue? And another reasonably prominent left-of-center pundit piped up and said, well, for my part, the reason I don't talk about it is it seems really complicated. I don't feel like I have a good grasp on all the science, and so I just don't feel qualified to go out and say and assert things publicly about it. And now anybody who has ever so much as mentioned climate change on television or on the internet will understand why this person thinks the way they do. Anytime you mention it, the hordes descend, bearing complicated stories about the medieval ice age or sunspots or water vapor. And you know, there's a lot of myths about climate change born by these climate skeptics. But to debunk those myths, you have to know, you have to go online and research and read and be able to respond to them in detail. And a lot of people just find that prospect dreary, and so they don't bother. And this, of course, drives me crazy. So I piped up on Twitter and said, you know, climate change is not actually that complicated. What you need to know to be able to speak out publicly about it, just about the basic structure of the problem, is really not that complicated. I could explain it to you in 15 minutes. So let this be a lesson to you. Don't go talk smack on Twitter unless you're willing to back it up. So one thing led to another, and here I am with 15 minutes to explain climate change to you. So let's get started. Why is the Earth not a cold, dead rock floating in space? The reason is that it is enveloped by this tiny, tiny, thin layer of gases and chemicals that we call our atmosphere. So the sun's energy, rather than just coming down and bouncing right back off, it comes down and is held close to the surface of the Earth for a while and then bounces off. And that simple process is why we have evaporation and precipitation and photosynthesis and life on our planet. So scientists discovered well over 100 years ago that the atmosphere and the systems on the Earth are in this dynamic relationship, and you can change the chemical composition of the atmosphere and hold more of the sun's energy for longer. The energy still has to escape, of course, but in the meantime, it will cause changes in these biophysical systems of the Earth. And you often hear people say the Earth has always changed, the climate has always changed, and that's true, it has. This relationship between the atmosphere and the systems, they go through cycles, but these cycles have typically taken hundreds of thousands of years, millions of years. The key thing to know first is that for the last 10,000 years on Earth, the climate has been relatively stable, unusually stable. And by stable, I mean temperature has varied, it's gone up and down, but it's stayed in a fairly narrow band of about plus or minus 1 degree Celsius. And all of advanced human civilization has taken place during this 10,000 years. The development of agriculture, the written word, the wheel, the iPhone, everything we know, everything we have built, we have done in this period of relative climate stability. So what we've been doing for the last couple of hundred years is digging up carbon out of the Earth and throwing it up into the atmosphere and changing the chemical composition of the atmosphere, like has happened in the past, except for way, 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 way faster. In geological time, the blink of an eye, we are substantially changing the chemical composition of the atmosphere, and all of climate science has been about what's going to happen. What is the Earth going to do in response to this? And so we've already seen that the process is underway. We have measured, we have witnessed, observed with our eyes and our thermometers about a 0.8 degree Celsius rise in global average temperature since before the industrial age, since before we started digging all this carbon up. And this may not seem like a lot, less than 1 degree Celsius, but the thing to know about it is these greenhouse gases we throw up stay in the atmosphere for a very long time. There are very long time lags involved here. So this 0.8 degree temperature rise is a response to what we were doing 50 to 100 years ago. And what we see in the first half of this century will be a response to what we've done the last 50 years. And what we see in the latter half of this century will be a response to decisions we make today. So the question is, temperature is rising. How high does it have to rise before we need to worry, before we're in danger, before bad things start happening? The typical answer to this question has been 2 degrees Celsius. Anyone who has followed climate change discussions knows that this 2 degree number has taken on a kind of iconic quality. Typically, climate scientists who model impacts of what's going to happen model a 2 degree Celsius rise. Typically, economists who try to model what it will cost to do something about climate change, or what it's worth, or what various policies will cost, model 2 degrees centigrade. So obviously, what counts as not dangerous versus dangerous is not a hard scientific question. It's a political question, and this was a political decision to take this 2C number, mainly made by European climate negotiators well over 10 years ago. And it's just sort of stuck since then. All the countries involved in climate negotiations have basically signed on saying, yes, this is what we want to avoid, 2 degrees centigrade temperature rise. The bad news on this 2C number is twofold. First of all the latest science done in the last 10 to 15 years has pointed to the conclusion that those impacts we thought were going to happen around 2 degrees centigrade are in fact going to happen much earlier than that. The climate is more sensitive to this added greenhouse gases than we thought. So if those were the impacts we were worried about, then the real threshold of safety ought to be something like 1.5 degrees centigrade. James Hansen is the climate scientist most famously known for raising these warnings, but it's a growing scientific consensus that 2 degrees is in fact dangerously high, which is bad because we are almost certainly going to blow past 2 degrees Celsius. There's some reason to believe, a recent study said that even if we stopped our climate emissions tomorrow, we're still going to get more than 3 degrees this century just from momentum from the previous emissions. But stopping at 2 degrees now would take a level of global coordination and ambition that is nowhere in evidence. So a lot of climate scientists don't really want to tell you this because they don't want to depress you, but I'm just a blogger, so I'm happy to depress you. 2 degrees Celsius is probably off the table. So then the question becomes, well, what does it look like if temperature goes higher than that? What would, say, 4 degrees Celsius look like? Oddly, there hadn't really been a lot of concerted scientific attention to that question because climate scientists honestly thought we wouldn't do that to ourselves. But we are doing it to ourselves. So in 2009, several climate change research groups in England drew together a group of scientists, commissioned some papers, and had them really take a hard look for the first time. What would 4 degrees Celsius look like? There were a lot of papers, a lot of equations, a lot of talk and complexity. I have helpfully paraphrased it here for you to make it easier to grasp. 4 degrees Celsius temperature rise would look ugly. Among other things, that would be the hottest the Earth has been in 30 million years. Sea levels would rise at least 3 to 6 feet, and this excludes some really tail-end possibilities, but 3 to 6 feet at least. And persistent drought would cover about 40% of the currently occupied land on Earth, which would wreak havoc on agriculture in East Asia, in Africa, South America, Western US. All this combined would produce hundreds of millions of people who had been driven from their homes, either by their cities being swamped by sea level rise or by hunger or by all the attendant ills that come along with those things. And to boot, probably somewhere around half of the known species on Earth would go extinct. This question of pinning down the exact number of species is very difficult. This is very much an approximation, but some substantial chunk of life on Earth would be wiped out. The final bit of bad news, that's not true, there's more bad news to come. A middle bit of bad news is that according to a recent paper by the International Energy Agency, we are currently on track, if we keep doing what we're now doing, if we go on with business as usual, as it's called, we are now on track for 6 degrees Celsius temperature rise this century. Something, 5 to 7. These are obviously estimations. So if 4 degrees is hell on Earth, I'll let your imaginations fill in the blanks on 6 degrees. But one danger that comes up when we contemplate going this high with our temperature is the possibility that climate change will become irreversible. I think when people typically think about climate change, they think, oh, temperature's gonna rise X amount, circumstances will change, some places will get warmer, some places will get wetter, we'll adjust, we'll move our farms around, people will migrate from one city to another, we'll get resettled, and we'll go on with life. The really dangerous possibility is that what are called, the Earth has several of what are called positive feedback systems. So for instance, in Siberia, there's this permanent ice, the permafrost, and it contains a bunch of methane in it. As it melts, it releases that methane. The methane causes more warming, which melts more ice, which releases more methane. It's a self-sustaining process. Or sea ice melts. Ice is white, it reflects energy. When it melts, it becomes dark blue and absorbs more energy, which heats the oceans, which melts more ice, which creates more dark surfaces. You see, there's a number of these systems that are self-perpetuating. And the great danger of climate change that towers above all these other more specific dangers is that these positive feedback systems will take on a momentum of their own that becomes unstoppable. And human beings will lose any ability to control it at all, even if we stop all our climate emissions on a dime. Will that happen at 2 degrees? Probably not, though there's a real chance of it, and there's a lot of debate about that. Will it happen at 4 degrees? Well, it looks a lot more likely at 4 degrees. Will it happen at 6 degrees? Almost certainly. So if we continue on our present course, climate change will probably take on a life of its own, spiral out of control, and according to a recent paper, by 2300, we could see temperature rise of up to 12 degrees centigrade. Now, if that happened, something like half the Earth's currently inhabited land would become too hot to survive on. And when I say too hot to survive on, I don't mean it's difficult to grow beans or air conditioning bills are inconveniently high. I mean, if you go outside, you die of hotness. I mean, places that were an average of 80 degrees Fahrenheit will now be an average of 170, 180 degrees Fahrenheit. Literally too hot for human beings to go outside and survive. So, will there still be human civilization under those circumstances? Who knows? I mean, maybe we'll live in underground climate-controlled caves, maybe we'll grow food in test tubes, but that wouldn't look anything like Earth as we now know it. It would look a lot more like Newt Gingrich's moon colony, assuming any human beings, or at least enough to make a civilization, survived in those circumstances. So, when I say climate change is simple, I know this has been bugging you. You're not used to thinking in Celsius, those strange European metric temperatures. So here's good American Fahrenheit. It's just as ugly. So this is what I mean by climate change being simple. There are many complicated and fascinating discussions to be had about what to do about it, or about what effect our actions might have on the climate and when, or which policies are best based on cost-benefit analysis. There's complexity, plenty of complexity for those of you who like complexity. But we now know to a fair degree of certainty that if we keep doing what we're now doing, we will face unthinkable catastrophe. That's the bumper sticker, that's the take-home message. And that, you know, saying, I don't want to talk about that because I don't know the ins and outs is like saying, I don't want to raise alarms about Hitler's army being 100 miles out because I don't know the thread count of their uniforms, or I don't know the average calorie intake of a German soldier. You don't need to know those things to be scared that the army's on the march and to raise alarms about it. Similarly, if we keep doing what we're now doing, we are screwed. This we know now. To stabilize temperature, and I don't mean stabilize temperature at 2 degrees or 4 degrees or 6 degrees, I mean to ever have a hope of ever again having a stable temperature of any kind, global climate change emissions need to peak, stop growing, peak, and start falling rapidly in the next 5 to 10 years. Every year we do not get started on this, we add, according to the International Energy Agency, an extra $500 billion with a B dollars to the price tag of what it's going to cost us to do this eventually. Every year we wait, that's $500 billion down the drain. Now, you and I look around at current politics, particularly US politics, and massive, coordinated, intelligent, ambitious action does not strike us as particularly plausible. In fact, it might strike us as impossible, but that is where we are, stuck between the impossible and the unthinkable. So your job, anyone who hears this, for the rest of your life, your job is to make the impossible possible. Thank you.